All right, open up your book to section 8-3. We're on page 397 in your book, and the title of this section is The Other Composite Argument Properties. The objective for this section is for trig functions f. We want to derive and learn the following properties. For f of the opposite of x in terms of f of x, those we learned were our odd and even properties. Or f of pi over 2 minus x in terms of functions of x. Those we learned are our cofunction properties. And f of a plus b and f of a minus b in terms of functions of a and functions of b, and those are the composite argument properties, which is what we're going to focus on here in this half of the section. All right, so let's go through our 6 composite argument properties. We saw these at the end of our notes there from the previous section, and we're going to go through and prove these actually. So the first property is the cosine of the quantity a minus b is equal to the cosine of a times the cosine of b plus the sine of a times the sine of b. And actually the proof for this we've already done. So I'm just going to say C notes from section 8.2. You've already seen that proof there. We went through and we sketched 2 angles, A and B, and we measured, we marked a couple points on a unit circle. We measured that distance D between those 2 points. We rotated that angle so it was in standard position, and we did the same thing again, and we went through all the steps that are necessary to prove that. So we don't need to go through and prove it again, but that's how you prove that first property. The good news is once we prove that property, I can use it or use it to help me prove the next property and the next one after that, which is what we're going to do here. So the next property is the composite argument property for cosine of a plus b. And the cosine of a plus b is equal to the cosine of a times the cosine of b minus the sine of a times the sine of b. So then the question is, well, how do we go about proving that? Well, again, the nice thing is we've already proven that first property, so we can use it to help us prove this one. So we've got the cosine of a plus b. I'll start with that on the left side. And over here on the right side, I'm going to try to go through algebraically or using some trig properties, whatever I need to, in order to come up with what I see over there on the right side. So I have the cosine of a plus b. Well, the first thing I want to do is rewrite this as subtraction because I have a property that we just set up above, we've already proven, and that property was for a difference of 2 arguments. So I can rewrite this as the cosine of a minus the opposite of b. I can change addition into subtraction. And again, the advantage of doing that is now I can use this property that I have up above here. I know that the cosine of one quantity minus another quantity can be rewritten that way right there. So we're going to do that. So I've got the cosine of the first angle, which is a, times the cosine of the second angle, which is the opposite of b. And then we add the sine of the first angle, which is a, times the sine of the second angle, which is the opposite of b, which gets us pretty close to the property we're trying to prove up above there. But I need to get rid of those negatives inside of those trig functions. I got to get rid of the opposite of b somehow. So I got to think about some properties that I've already used or proven for what cosine of the opposite of b is equal to. Well, in the first half of this section, we talked about the odd and even properties of our trig functions. Cosine, I know, is an even function. So because it's even, I can rewrite that as just the cosine of b. And the sine of the opposite of b, since sine is an odd function, I can rewrite that as the opposite of the sine of b. So let's use our odd and even properties here then. We've got the cosine of a times the cosine of just b. Again, that comes about because of our even property for cosine, plus the sine of a times, and then for this, it's going to be the opposite of the sine of b. So I'm going to put that in parentheses, the opposite of the sine of b. Again, that's using my odd property for the sine function. All right, so let's just rewrite this. We'll put that negative sign that we have there out in front of the first sign that we see there. So we've got the cosine of A times the cosine of B, and then minus the sine of A times the sine of B. There we go. There's our property. So using the first property that we've already proven, along with our odd and even properties, we're able to show the cosine of A plus B is equal to this. Very nice. All right, let's continue with these. And again, we're going to tackle these one at a time here. Now I have the sine of A minus B is equal to the sine of A times the cosine of B minus the cosine of A times the sine of B. So let's start this out like we did with the previous one here. We'll just write down our property that we have here, or not our property, we'll write down the left side of this property. And what I would like to do is use the previous two properties from the previous slide there to help me prove this. Is there any way that I could use those? Is there any way that I can go from sine to cosine? Again, think about the properties we've learned here in this section, and oh yeah, there is a property that lets me go from sine to its cofunction, cosine. It's my cofunction properties that allow me to do that. I can rewrite this as the cosine of pi over 2. I'm going to do this in radians, but obviously this would also apply in degrees if you were working in those units. But it's the cosine of pi over 2 minus that angle of A minus B. Now before I use the composite argument property, which is where I'm headed with this, I'm going to reassociate these terms that I've got here. So I'm going to rewrite this as the cosine of the quantity pi over 2 minus A will be my first argument. And I'm distributing that minus sign through to get this to be a plus B here. All right, so I've got the cosine of one angle plus some other angle. We already have a property that tells us how we can rewrite that. We just proved that on the previous slide, in fact. So let's just rewrite that, what it's equal to. The cosine of the first angle, pi over 2 minus A, times the cosine of the second angle, which is B, and then minus, remember the sign changes here for cosine, minus the sine of the first angle, pi over 2 minus A, times the sine of the second angle, which is B. That's pretty close to what we're trying to prove, but I need to get rid of these pi over 2 minus A's. I got to somehow get rid of those. Is there a way that I can rewrite this? Pi over 2 minus A, oh, that's a complementary angle to the angle A. Yeah, I could use my cofunction properties again to rewrite those. The cosine of pi over 2 minus A, I can rewrite that as just the sine of its complementary angle, the sine of A. And for the sine of pi over 2 minus A down here, I can again do the same thing. Use the cofunction and use the complementary angle and rewrite this. Okay, so let's rewrite it that way. So instead of the cosine of pi over 2 minus A, this is the sine of A times the cosine of B, and then minus, instead of the sine of pi over 2 minus A, it's going to be the cosine of A times the sine of B. And actually, right there we go. There's our property that we are trying to prove. Sine of A times cosine of B minus the cosine of A times the sine of B. All right, the fourth property is just the sum of A and B, the sine of A plus B. And now that we've done this for cosine, we should have a pretty good idea of how we're going to go about this. That if I can rewrite this as a difference, I can use the property that I just proved right up above here. So the sine of A plus B can be rewritten as the sine of A minus the opposite of B. Okay, so let's use the property from up above here. We just proved that if I have the sign of one quantity minus another quantity, I can rewrite that as this difference of these two products, sine of A cosine of B minus the cosine of A sine of B. So let's rewrite it that way. This is equal to the sine of the first angle times the cosine of the second angle, the opposite of B, and then minus the cosine of the first angle times the sine of the second angle. All right, and now I've got to get rid of these opposite of b's, but now again, because of the work I did on the previous slide here, I got a good idea of what I'm going to use to do that. But I'm going to use my odd and even properties to replace that guy right there with cosine of b. And this guy right here, he can get replaced with the opposite of the sine of b. All right, so let's do that. So we've got the sine of A times the cosine of B. Since it's an even function, it can be replaced with just cosine of B. And then I've got minus the cosine of A times the opposite of the sine of B. I'll put that in parentheses so I get that negative sign distributed correctly here. And it doesn't look like I'm subtracting that sign at the end. And now let's just rewrite this. The first part of this will stay the same, the sine of A, cosine of B. But let's take that negative sign that I have here with sine and pull it out front here, so that becomes a subtracting and negative as addition. So it's plus the cosine of A times the sine of B. Hey, look at that. There's our property that we're trying to prove. Sine of A plus B is equal to sine of A cosine of B plus cosine of A sine of B. Very nice. All right, so we've got two more properties here dealing with tangent. So remember that we said that the tangent of A minus B is equal to the tangent of A minus the tangent of B, all over 1 plus tangent of A, tangent of B. And we kind of hinted how we're going to prove this when we were talking about this property in the first section. We said that we have a quotient property for tangent. Tangent can be rewritten as sine over cosine, and that's what we're going to do here. So let's start out with the tangent of A minus B on the left side here. And we know that is equal to the sine of A minus B divided by the cosine of A minus B. In fact, we just showed what the sine of A minus B is equal to on the previous slide. And we had previously already shown what the cosine of A minus B is equal to. So let's just use those properties now to rewrite our numerator and denominator. So we've got the sine of A minus B. That's the sine of the first angle times the cosine of the second angle. Remember that the sine stays the same with our sine property here, so it's minus. And then it's the cosine of the first angle times the sine of the second angle. There we go. And that's all divided by, do the same thing in the denominator now. It's the cosine of A times the cosine of B. Now with cosine, the sign swaps, so instead of subtraction, it's addition now. And it's the sine of, sine of A, sine of B. All right, now we're trying to get this into the form that I see up above there that's in terms of tangent. So in order for that to happen, I've got to somehow introduce some sines divided by cosines in order to make that happen. So I've got to actually multiply by a clever form of 1 here. And it won't be quite obvious why we're going to multiply by this initially here, but we'll see that we end up with the result we're looking for when we pick this. Again, this would have to be something you kind of play around with a little bit to figure out that this is the quantity I want to multiply by. But it turns out if I multiply by 1 over the cosine of A times the cosine of B, all over 1 over the cosine of A times the cosine of B. Now the hint as to why I might do that is because I'm trying to get sine over cosine. I need cosines in the denominator. That might be one way you'd think about doing that. But let's see what happens when we multiply this out. So we're going to distribute that to the two terms that I see in the numerator as well as the two terms that I see in the denominator. So I take this guy right here, and I'm going to multiply him by this guy here. In fact, I'm going to write it in that quotient form to start off with. So I'm going to write it as the sine of A cosine of B. That is what I already have there in the numerator. And I'm going to divide it by this clever form of 1, or the numerator of that. So when I multiply that, I end up dividing by just the cosine of A cosine of B. All right, so I've distributed this guy here to that first term. I've multiplied those two together. Do the same thing for the next term here. So the numerator, again, is this cosine of A sine of B. And that's all divided by the cosine of A times the cosine of B. Let me give myself a little bit more room here. All right. Got a little more room here to deal with, and now we got to divide all this by the denominator. So in the denominator, I'm going to take, again, this 1 over cosine of A times cosine of B and multiply it by this. So this cosine of A cosine of B is in the numerator, and then my clever form of the one that I'm multiplying by, cosine of A cosine of B. You'll notice that keeps showing up over and over again for each one of these fractions that I've got here. And then minus, finally, the sines that I'm multiplying times this 1 over cosines ends up giving me sine of A sine of B all over the cosine of A cosine of B. All right, now it definitely doesn't look much better with what we have right now. Looks like we've made this thing more complex. But if you look at what we have here, a lot of stuff will cancel out. I've got a cosine of B and a cosine of B. Those will cancel each other out. Here we've got a cosine of A and a cosine of A. Those cancel each other out. Here we've got cosine of A and cosine of A, and actually cosine of B and cosine of B. Those cancel out. And in the last part here, well, nothing cancels out. Okay? And then furthermore, if we look at what we're left with, sine of A over the cosine of A, that's better known as tangent of A. Here we've got sine over cosine again. That's better known as tangent. Everything cancels, so when we cancel everything out there, we're going to be left with a 1. Maybe I'll mark that we remind ourselves we're left with 1 there. And here I've got sine of A over cosine of A. That's a tangent of A. Here we've got sine of B over cosine of B. That's tangent of B. So we can use all of that to rewrite this now in the following way. So the first part here, we're left with just the tangent of A. In the second part, we're not adding, we're subtracting there. We've got sine over cosine of B, so that's tangent of B. All this stuff canceled here, so we're left with a 1. And then it should be, oops, I got the wrong sign there. Man, I messed up the sign again there. This was negative over a positive. I should have a minus over a positive is what I should have here. So this should be plus. And then here we've got the sine over cosine. That's tangent. There's another tangent. So it's the tangent of A times the tangent of B. And right there is our property that we were trying to prove up above there. All right, we have one last property. And again, with all the work we've done up to this point, we should have a good idea of how we're going to go about proving this one. The last property here dealing with the difference, the sum here, that if you have the tangent of A plus B, that I can rewrite that as the tangent of A plus the tangent of B all over 1 minus the tangent of A times the tangent of B. Now we could do it very similar to what we just did up above, but I'm going to do it similar to how I did the other problems there on the previous slides for the sum. We just use our previous property to prove this. I'm going to rewrite this as a difference. So let's do that. If I take the tangent of A plus B, I can rewrite this as the tangent of A minus the opposite of B. And now I can just use the property that I have from up above there. So I can rewrite this as the tangent of A, and then minus the tangent of the opposite of B, all over 1 plus the tangent of A times the tangent of the opposite of B. And again, the last step of this is now to use your odd and even properties. Tangent is an odd function. So since tangent is an odd function, we can replace the tangent of the opposite of B with the opposite of tangent of B. So what do we end up with here? I've got tangent of A, and then minus, it's going to be the opposite of tangent of B. And in the denominator, I've got 1 plus the tangent of A times the opposite of the tangent of B. And I guess one last time here just to rewrite this and clean it up. We'll take these two negatives and combine them. Subtracting the negative is the same as addition. Tangent of A plus the tangent of B in the numerator. And 1, bring this negative out front, we'll have 1 minus the tangent of A times the tangent of B. There we go. We've proven all 6 of those properties. All right, so now let's try using these properties here in an example. Look at example number 1 on page 402. Example 1 says to solve the equation for x in the interval from 0 to 2 pi. So they gave us this equation. Sine of 5x times the cosine of 3x minus the cosine of 5x times the sine of 3x, and they were setting this equal to a value of 1/2, it looks like. And again, the domain that they've given us to work with is from 0 to 2 pi. All right. The first thing to notice here, when I look at this left side, is this looks a lot like some of the properties we were just talking about. But I've got a sine times a cosine minus a cosine times a sine, and the arguments are 5x and 3x in each of those cases. So this looks a lot like our composite argument property for sine. In fact, that's what it is. I can rewrite this as the sine of 5x minus 3x. That's what the sine of 5x times the cosine of 3x minus the cosine of 5x times the sine of 3x is equal to. That's the property we're just looking at. So I'm just setting this equal to 1/2. Of course, we can simplify that now. 5x minus 3x, that's better known as 2x. Sine of 2x is equal to 1/2. And now we're to a equation that we solved many times now. I have a sinusoid set equal to some number. Let's solve that. We're going to use arc sine to do that. So we have 2x is equal to the arc sine of 1/2. So 1/2, that's a very good one. Let me fix that. And then divide by the 2, so you have x is equal to 1/2 of the arc sine of 1/2. All right, so let's replace arc sine with what it's equal to. I think I'm going to leave the 1/2 out front for just a moment, and we'll just work with arc sine, and then we'll go ahead and distribute the 1/2 through in a second. So arc sine is the sine inverse of 1/2 plus, and this is in terms of radians here, so plus 2 pi n. And then pi minus the sine inverse of 1/2 plus the 2 pi n. And now let's go ahead and distribute the 1/2 through. I've got to distribute it to every single term that I see here. I've got to take this 1/2 and it's got to get distributed to this and this, as well as down here, this, this, and this. There's 5 terms total I got to distribute that through to, so don't leave off a term when you do that distribution there. Let's see what we end up with. It's still a piecewise function, of course, but it's going to be 1/2 sine inverse of 1/2 plus pi n. And then it's going to be 1/2 or pi, or just pi over 2, I'll write it that way, minus 1/2 the sine inverse of 1/2, and then again plus the pi n. Now you could distribute that 1/2 through there right when you go from arc sine up here to using its definition to rewrite it. If you're comfortable distributing all the way through there, that's fine to do, but just remember that 1/2 gets distributed to everything. All right, the last thing we need to do is find out what are the values of n that we're going to see here. When I look at this function here, sine of 2x equals 1/2, I can graph that. Sine of 2x, that means that the period is 2 pi over 2. The period is pi, and we're looking at the interval from 0 to 2 pi, so I'm going to see 2 periods of this thing. If you're not comfortable graphing this, then grab your calculator and graph it, but we should be able to graph this sine function here. Something like this. Here is going to be pi, and here is going to be 2 pi. Again, the period of this is pi. And we're setting it equal to a value of 1/2, so we'll say 1/2 is somewhere around here. So here's our solutions that we're looking for. There's 1, 2, 3, 4. We're expecting 4 solutions because there's 2 solutions in each period. And so our starting point, the phase displacement of this, we take a look at that. The phase displacement, you're not subtracting anything from the x there. In other words, the phase displacement is 0, so we're starting at x equals 0 with n equals 0. So right here is where n is equal to 0. You're going to move forward from there to get the positive sine inverse solution. You'll continue moving to the right to get the pi minus sine inverse solution. I know ours is 1/2 pi minus 1/2 sine inverse, but in general, this is what we hit. Here's where n is going to be equal to 1. Here's our sine inverse solution. Keep moving forward, and we hit our pi minus sine inverse solution. So it looks like we use the same values of n in each of those solutions. So we're going to have n is equal to 0 and 1 here, and n is equal to 0 and 1 here. There is algebraically our 4 solutions to that equation. All right, and that right there is the end of section 8-3.